I want to start off this video talking about the difference between a discrete variable and a continuous variable. And in a nutshell, continuous variables are uncountable. There are infinite possibilities they could be, while discrete variables are countable, and there's only a finite number of possibilities they could be. Some examples of discrete variables would be how many cars pass through an intersection. You could stand there and just count, and it could be one or two or three and so on. It has to be whole numbers as you count the variable. Another example is how many calls someone makes per day. You would again just count with whole values how many calls they make. For continuous variables here, how fast a car is going. So that would have to be something you measure. We're going to measure these instead of counting because um, there are infinite possibilities here. It could be any fraction, any decimal. A car could be going 55 miles an hour, or a car could be going 56, but there's infinite, just in between those two, there's infinite possibilities. It could be 55.23 or 55.67 or 768 or 55.99994 miles per hour. So as you can see, the possibilities here are endless. And I've only talked about the values between 55 and 56. So if you're measuring something and it can take on any decimal or fractional value, it's uncountable, it's infinite, and that's when it's a continuous variable. So now we're going to start talking about probability distributions. And really here we're looking at the distribution of all the possible values that our variable can be. And then we're going to look at the probability of each of those values. That's the likelihood that each different value will occur. So in this example, it's a psychologist. He's given people a score on from 1 to 5 on how aggressive they are. 5 is extremely aggressive, 1, they're extremely passive. So the different values we could possibly have are just 1, 2, 3, 4, or 5. So this is definitely discrete because it's countable. There's just 5 options. So this is a discrete probability distribution. In graphical form, we always have our values on the x-axis horizontal, and then the height of our distribution shows how likely or how probable each event is to occur. So with discrete, it's going to look like a bar graph because there's a fixed number of possibilities, and you just draw a bar as high as the probability is for each different outcome. So here we can see that 3 was definitely the most probable, and then it's kind of symmetric, tailing off evenly to both sides. Here's what a table would look like for a discrete probability distribution. You have the different options listed out and the probabilities of each option. Each probability is always between 0 and 1. Probabilities, that's true of every probability. It has to be between 0 and 1. And then all the probabilities added together will always equal 1 because something has to happen. So all those probabilities have to add up to 100%. And you can create something like this using what we know about frequency distribution. So if you will look up here, we have a frequency distribution, the 5 different possibilities someone can score on this scale 1 to 5, and then the frequency of each of those outcomes. And so if you add these up, there's 150 people total, and just divide each frequency by 150. You can see all the math here. Divide each thing by 150 and you get the relative frequency, which is also the probability of each of the different outcomes. And so once you have each of those outcomes, put them in table form or put them in a graph form here, a histogram, and we see the probability distribution. And now let's talk about finding the mean of a discrete random variable. And you're going to take each possible outcome, each x, and multiply it by its probability, and then add all those up. And so working with that same example we just had, so you should recognize these numbers here, are on a scale of 1 to 5, that's what you can be rated, and here was the probability of each of those outcomes. So you would just take 1 times 0.16, 2 times 0.22, and so on, and then add all those up. And when you add all those up, we call that well, that is the mean then of our discrete random variable. Now you may be thinking, well, 2.9 isn't even a possible score. You have to be either a 1, a 2, a 3, or 4, or 5. So how do we interpret this mean? What we would interpret this as is if we took a bunch of people, gave them a rating, and then we averaged all their ratings, this is what we would anticipate the rating would come out to from all those people. And you'll see that we also call that the expected value. This is the exact same formula. The expected value is the mean. Remember, mean is a measure of the center of the data. It's in the middle. It's what we kind of expect to happen, or what we anticipate to happen. So expected value and the mean of a discrete random variable have the same formula and are the same exact calculation. Here's the formula for variance and standard deviation for discrete variables, and again working with the same example. You have to have the mean first. You take each value, subtract the mean away, then we square those values, and then we multiply that squared value by the probability. So by column 1 here, the 0.16. So after you've squared it, multiply it by its probability. And then once again, we're just going to sum those up. And when we sum all them up, add them all up, we get the variance. And like always, standard deviation is the square root of the variance. So we would just take the square root of that value to get our standard deviation. For the remainder of this video, we're going to be talking about the binomial distribution. And bi means 2. So these are experiments that only have 2 possible outcomes, and we're going to call one outcome success and we're going to call the other one failure. A couple of examples. One's you shoot a basketball, you either make it or miss it. There's 2 outcomes. You could be in the medical field researching the flu, and you could ask people whether they have the flu or not. There's 2 outcomes: have the flu or you don't. Here are all the requirements for it to be a binomial experiment. Number 2 is what we just talked about, that there's 2 possible outcomes, either success or failure. Number 1 says we're always going to count exactly how many trials we're running. In terms of shooting a basketball, that would be how many shots are we going to take total. Number 3 says probability of success isn't going to change from shot to shot in our basketball example. And number 4 says what we're actually trying to count here, what our distribution is going to show, is the number of successes. So if we said we were going to take 20 shots with the basketball, our random variable would then be all the values from 0 to 20, because that's the possibilities for the number of successes we could have. We could make 0 shots or 1 shot, all the way up to making them all at 20 shots. This is where you need to start every binomial problem, is identifying what these values are. So whenever you read the problem, N stands for the number of trials. Identify how many that is. P stands for the probability of success, and those values are usually told to you in the problem. Q is the probability of failure. So if success had 60% chance, then failure happens 40%. And it shows that here. You just do 1 minus your success. That gives you the failure. And then X is usually what we're trying to figure out here, is the probability for different values that X can be for a different number of successes. It's the number of successes. Here's the formula we use to calculate the probability of a certain number of successes out of N trials. And I'm going to show how to do it in Excel. It's really easy in Excel compared to trying to work out this formula by hand. But this formula is all based off of the multiplication rule of probability, so I'll touch on that briefly. We're looking at a rotator cuff surgery example here. 90% chance of success. So our chance of success is 0.9. And the surgery is performed on 3 patients. Find the probability of the surgery being successful on exactly 2 patients. So always start off by identifying your variables here. So probability of success was 90, which means failure is 10%. There's 3 total patients, and our X here that we're trying to find the number of successes is the probability that 2 out of the 3 were successful. And so what you want to enter in Excel is this formula here, equals binom.dist, and then you type in your number of successes you're looking for out of the total number there are, and then the probability of success. And you use false for an exact number. So if we want to know the probability of exactly 2 out of 3 successes, we use false. You use true for that number or less. So watch how it changes. Binom.dist, 2 out of 3.9, true. The probability is a little higher now because now this is calculating the probability of either 0 people successful, 1, or 2. That number that we enter 2 or anything less than that. Here when we put false, it just gave us only the probability of 2 out of 3 being successful. And notice the only thing that we've left out here is the probability of 3 successes. So let's just look at what that would be. And I'm going to save some time by copy pasting here and then just changing it to 3 out of 3. So it's 729. And notice how these two values add up to 100% because now we've covered every possibility. This is the probability of 0, 1, or 2 happening. And this is the probability of exactly 3 happening. And I mentioned how this is all based on the multiplication rule of probability. When you're trying to find the probability of multiple events in order, like success, success, failure for 2 out of 3 patients, you just multiply the probabilities of each step together. So success is 90% times success 90% times failure 10%. So multiply those together and you get your answer. Now, 2 out of 3 successes could be the first 2 successful, the first and the last successful, or the last 2. Those are the only 3 options. And the probabilities for each of those is shown here again with the multiplication rule of probability. If you add those 3 things together, you get 0.243, and that's exactly what we got here when we typed in 2 out of 3 successes, 90% false. For binomial situations, we have these formulas for mean, variation, and standard deviation. So always start off by finding N, P, and Q, listing out what they are for any problem, and then just plug them in here to get your mean, variation, and standard deviation, like always, is just the square root of the variation. And we're going to wrap up this video with an example. So a survey of U.S. adults found that 62% of women believe that there is a link between playing violent video games and teens exhibiting violent behavior. You randomly select 4 U.S. women and ask them whether they believe that there is a link between playing violent video games and teens exhibiting violent behavior. And always start off each problem by identifying these values. So in here is the total number of women that we're going to be asking, and it says we're selecting 4 total. The probability that each person says that there is a link between video games and violence, and we're calling that success, that they do think there's a link, it's 62%. And so 1 minus that is then the probability of failure. And so the first question we're asking is to find the probability that exactly 2 of them respond yes. So exactly, for an exact number of successes, we use false. So exactly 2 out of the 4 with a 62% probability of success, we would enter this formula. And this is the probability that exactly 2 of the women say yes, that there is a link. For our next problem, we're looking at the probability that at least 2 of them respond yes. So think of all the possible outcomes. You ask 4 people, it can either be 0, 1, 2, 3, or 4 responding yes. So at least 2 would be these ones I've colored blue. 2, 3, or 4 responding yes. Now the fastest way to do this is to enter the formula like this. What I'm going to do is calculate the probability of 0 or 1 and then subtract that probability from 100%. And that leaves me then with the probability of 2, 3, or 4 by the complement. So I'm doing 1 minus, this is the probability of 1 or less because I'm using true. So this is going to subtract away the probability of 0 and 1, which leaves me with 2, 3, and 4. And the other longer method would be to actually take the probability of exactly 2, exactly 3, and exactly 4 and add those together. You're going to get the same result. So exactly 2 with the 2 in the formula, exactly 3 with the 3 in the formula, and exactly 4 using false each time since it's exact. And then if you just add those together, you get the same exact result as when you use the shortcut method by doing 1 minus.
fewer than 2 of them responding yes would be either 0 or 1 responding yes. So we use the formula with a 1 in there and true, and we get that result.